History of Vector Analysis, Episode 16, Maxwell's Treatise. You are here. Hey, it's old Doc Oler. Welcome back. In the previous episode, I discussed how Maxwell interacted with Tate to apply quaternion mathematics, and specifically the del operator, to Maxwell's field-based theory of electricity and magnetism. Maxwell was deeply taken with the inherently visual or geometric appeal of quaternions as single mathematical objects. He was convinced that the non-mathematical Faraday had been able to develop the mathematical law that now bears his name because he saw fields visually in terms of magnitude and direction rather than the more abstract X, Y, and Z components. Maxwell was a big fan of the visual, even though he could do algebra with the best of them. So, Maxwell was predisposed to something like Hamilton's quaternions. Maxwell had been aware of Hamilton's quaternions. Hamilton was a major figure, and even if you didn't buy his theories, you still had to be aware of them. Why didn't Maxwell take an interest in quaternions earlier? While it's difficult to say for sure, historian Michael J. Crow implies that this was at least in part due to the firm opposition to the quaternion approach of William Thomson. Thomson was a towering and intimidating figure, and his opposition to quaternions was well known. Now, Thomson, who co-invented field theory with his 1841 paper, written at age 17, opposed quaternions for several reasons. One of these was that he, Thomson, simply considered them unnecessary. Cartesian coordinates worked, and while quaternions sometimes offered a kind of notational shorthand that supported a compact way of writing sets of equations, they were not worth the additional effort. To use modern terminology, Thomson considered the cost-benefit analysis for quaternions to be strongly negative. Interestingly, Crow goes further and suggests that Thomson would likely have opposed any vectorial approach, including the one we use today. But Tate's clever development of the del operator in particular finally drew Maxwell in. The results were decidedly mixed, as we will see, but in 1873, years after he had completed the development of the entirety of his electromagnetic theory, Maxwell produced his magnum opus, his two-volume treatise of electricity and magnetism. The treatise is written in two different mathematical languages adjacent to each other. First, the Cartesian coordinate notation that he wrote the original papers in, and that was the standard of the day. And second, a version of the quaternion approach of Hamilton and Tate. Unfortunately for today's readers, neither of these languages is used much today, so perusing these books is not trivial. Maxwell was very productive in the 1870s, but he died of cancer in 1879 at the age of 48. His treatise was popular enough that he was working on a second edition when he died. This was completed by others and published posthumously in 1881. This is worth noting because Hertz did not demonstrate the existence of electromagnetic waves until 1887, and so those portions of the treatise that addressed such behavior in general were politely ignored up until that point. The two volumes together total about 1,000 pages. I have not read the entire thing yet, but I have read significant portions of it. I can tell you that it is as much a memoir as it is a treatise. There are details on the experimental hardware he used, the problems that he ran into with that hardware, how he overcame them. There are a lot of asides. Physics-wise, Maxwell makes extensive use of Lagrangian mechanics. It is well written, but it is not intended to be a textbook. Briefly, here is the top-level table of contents for Maxwell's treatise. It is divided into four major parts with a brief preliminary section. I'll come back to this outline in a moment. If you have been with me from the beginning, you may recall that in the very first episode I stated that the most important chapter of any physics textbook is Chapter 1. This is the material that the author not only expects you to accept as given, it also includes the math that he expects you to be able to do in your sleep going forward. Now, while I just stated that this treatise was not intended to be a textbook, it was aimed at his professional colleagues, not students, I will argue that this rule about Chapter 1 applies here as well. So, what is in Maxwell's preliminary section? What does he expect the reader to fully understand before he gets into magnetism, electromagnetic waves, and all that? Yes, he introduces a bit of calculus and even goes so far as to define the nabla operator. But for me, the thing that jumped out was Gauss's theorem and Stokes' theorem. Maxwell expected his readers to understand these theorems in vector form before he even introduced electrostatics in the form of Gauss's law. Okay? Troubled physics majors, FYI. Now for the other 950 pages. Part 1 of Maxwell's treatise is on electrostatics, electric charges that don't move, and the resulting time-independent scalar and vector fields that they create. The shorter Part 2 is what he calls electrokinematics, and it deals mostly with the properties of DC currents, amperes, conduction, Ohm's law, and that sort of thing. Part 3 is on magnetism and discusses both permanent magnets and solenoids, electromagnets. Part 4, the big guy, is what you get when you put the first 3 parts together. Electromagnetism, or as we generally refer to it today, electrodynamics. This is where Maxwell's equations appear in their non-modern format, along with the prediction of electromagnetic waves that detach from their sources and fly through space at the speed of light. Although Maxwell's treatise is not a textbook, most E&M textbooks today are organized along these lines. But this series is not about Maxwell's equations per se. It is about the history of vector analysis and how we got there. It is to this story that I will now return. As stated, Maxwell expressed the same math in 2 different languages in his treatise. The first, the Cartesian coordinate format, looks like this on the left. The quantities in the x, y, z directions are all assigned their own symbol and are treated independently. There are no ijk unit vectors anywhere. The upside of this notation was that it was standard at the time, so everyone working in the field was familiar with it. In addition to being long, one of the subtle downsides was that it burned through the letters of the alphabet really quickly, which became an issue when dealing with more complex problems. The second format, usually written in the treatise immediately after the Cartesian format, was a modified version of the Hamilton-Tate quaternion approach, with the period here in the middle representing what we today call the dot product. You can see that it is shorter, more compact. Less obvious, but no less important, is that this equation does not explicitly refer to any particular coordinate system, Cartesian or other. It is coordinate independent in this sense. Tate used Greek letters, alpha, beta, etc., to represent his vector-like quaternions. But Maxwell needed these Greek letters for other purposes, so he decided to use these Germanic script letters instead. This addressed the problem, but not very well. The downside of Germanic script letters is that they are difficult to read and distinguish, and even harder to write by hand, unless you're a calligrapher. Further, most printers did not carry them, a seemingly minor issue, but in a practical sense, a major one for anyone wanting to actually publish a paper using this new mathematics. Just to show you what Maxwell's equations look like in Maxwell's treatise in quaternion format, here they are. The first thing you notice, at least after the German script letters, is that there are a lot of them. Further, they are not simply the x, y, and z components of the 4 equations we use today. Okay, as an aside, I will note that they do not appear in a table like this on a single page. They are scattered throughout Part 4 of the treatise. I got this table from the reference shown at the bottom. Let me pause for a moment and ask, why do we use vector analysis for E&M today when we apparently don't have to? Some argue, both at the time and today, that it saves work, that you can do problems in 3 or 4 lines with vectors that it takes you a couple of pages to do in Cartesian coordinates. But this fact is true only rarely, and this was William Thomson's point. Here's a sample vector analysis problem I took from Schaum's Outlines, a great resource for science and engineering students even today. The problem states, quote, find the gradient of phi for, and then these functions. Look how simple it is to write grad phi, 2 symbols, right? And look, no reference to any coordinate system. This could apply to Cartesian, spherical, cylindrical coordinates, or any of the others. But, and again, this was Thomson's point, as soon as you want to actually evaluate the expression, you have to pick a coordinate system. Here, Schaum picks Cartesian, and then evaluate each of the 3 XYZ components individually. It just has ijk's instead of separate equations. Labor saved? 0. It may be aesthetically pleasing, but to Thomson, that's just form and not content. By the way, even though Sham doesn't approach the problem this way, you could solve the problem in spherical coordinates, as I show on the right. In this case, 2 of the 3 components are instantly identifiable as 0, and that saves you some labor. However, the formula for the gradient operator is different in spherical coordinates, and if there is any asymmetry at all in the real-world problem, the labor saving goes out the window. So if the vectorial approach doesn't really save much in the way of labor in practical applications, why was Maxwell so taken with it? After all, Maxwell was a practical guy. The answer, in his own words, comes from an unsigned review of another very short 1873 book on quaternions. Maxwell writes, "Now quaternions, or the doctrine of vectors, is a mathematical method, but it is a method of thinking and not, at least for the present generation, a method of saving thought. It calls upon us at every step to form a mental image of the geometrical features represented by the symbols, so that in studying geometry by this method, we have our minds engaged with geometrical ideas and are not permitted to fancy ourselves geometers when we are only arithmeticians." That is, Maxwell concedes Thomson's objection to quaternions and likely all vectorial approaches, that they do not offer the working physicist, engineer, or mathematician much in the way of a computational brick. Instead, Maxwell argues, their value lies in the visualization of fields, particularly vector fields. Maxwell finds the idea of being able to visualize the electric field at each point in space with a magnitude and a direction to be inherently valuable. Having said all of this, Maxwell was less than completely smitten with quaternions. In a sentence near the beginning of part 1 of his treatise, Maxwell states, "I am convinced, however, that the introduction of the ideas as opposed to the operations and methods of quaternions will be of great use to us." ... This damning with faint praise was missed by many readers at the time, but Maxwell expressed his concerns more explicitly in his correspondence with Tate. One of Maxwell's issues was what he referred to as the non-homogeneity of the quaternion or full vector product. As you hopefully recall, Hamilton had cleverly showed that the elegant, if not truly simple, results of multiplying quaternions whose real component was set to 0. It breaks up nicely into a scalar part and a vector part. Still though, that's a special case, right? What about the more general case where the A coefficients are not set to 0? Then you get all 16 terms when you multiply, and the results are, shall we say, less visually insightful. I mean, what do you do with this? Are there any practical applications for the full-blown product of 2 quaternions? Well, okay, there's that stuff about the rotation calculations, but even that didn't really shed much in the way of visual insight into the problem, which was Maxwell's motivation for using quaternions in the first place. This left a bad taste in Maxwell's mouth. Another thing that Maxwell disliked about the quaternion methods, as opposed to the quaternion idea, was noted by many others as well, and it was that damned minus sign in front of the quaternion scalar product. In Cartesian coordinates, the kinetic energy of a particle was given by the familiar expression 1/2 mv squared. The velocity might be negative in the sense that its direction was to the left rather than to the right, but the kinetic energy was always positive. Not so with quaternions. In quaternion notation, the velocity vector is expressed like this, and the kinetic energy is 1/2 m times the scalar part of the 0 real quaternion v times itself. But this, as we have shown, includes the squares of ijk, which, because they are imaginary, leads to a negative quantity. Maxwell was sympathetic to the Cartesians on this one and wrote in a letter to Tate, "Are the Cartesians to be denied the idea of a vector as a sensible thing in real life?" ... Crow points out that only one of the 4 books that Maxwell wrote after his treatise on E&M even mentions vectors, and there, in his 1876 book entitled Matter and Motion, quaternions were not mentioned at all. Still, the widespread appearance of quaternions in his treatise led many people in the field to consider them for the first time. This interest only increased after 1887 when Hertz proved the existence of electromagnetic waves. To sum up, the historian Crow writes, thus Maxwell's importance for the history of vector analysis is twofold. 1. He associated vectorial ideas with electricity in such a way that this linkage was maintained. And 2, he to some extent outlined the form that a suitable vector analysis should take. However, as we have seen, both the Cartesian and the quaternion methods had drawbacks. In his correspondence with Tate, Maxwell implied that someone ought to come up with a better solution. Next time, I'll show you how this challenge was independently accepted by two guys named Josiah Willard Gibbs and Oliver Heaviside. See you then.